In this video, we're going to look at graphs of derivatives. We can sketch a graph of f prime at x from a graph of f at x, remembering that f prime at x is the slope of the f at x graph. So, for example, if you have a maximum, a minimum, or flattened POI with a horizontal tangent, that will be a 0 on the graph of the derivative f prime at x. A cusp on the original function will be a vertical asymptote on the graph of f at x with opposite behavior on either side of the vertical asymptote. So what we'll see is a change in sign of the derivative function. A vertical tangent, which is not an asymptote, is a location where the slope of the original function is vertical. Remember, if you have the slope of a vertical line, this is undefined, and therefore it will be a vertical asymptote on the graph of the derivative function with same behavior on either side of the vertical asymptote. So here we'll have no change in sign. A point of inflection on the original function, well, a point of inflection will be either a max or a min on the derivative function, because remember that a point of inflection has to have the second derivative equal to 0, so that means it's got to be a max or min on the first derivative. Now, if f at x is increasing, then f prime at x will be positive. If f at x is decreasing, then f prime at x will be negative. So here we go, example 1. For y is equal to f at x, as graphed below, sketch a graph of f prime at x. Okay, so let's take a look at f is equal to 0. Well, f at 0 is a flat POI, and so therefore that is going to be f prime at 0 should also be 0. As you can see right here, f at approximately 1.2 is a minimum, so therefore f prime at 1.2 should be equal to 0. Let's create a sign table here. For x less than 0, 0 less than x, which is less than 1.2, and then x greater than 1.2. Let's look at the function, the original function. Well, for x less than 0, the original function is decreasing. And then between 0 and 1.2, it's still decreasing. But between 1.2 towards infinity, it is increasing. So if my function is decreasing, then my first derivative is negative. Again, first derivative is still negative, but over here, my first derivative is positive. Okay. The one thing that we see right here at about 0.75, I'm not sure if you can see this right here. Okay. But at f at 0.75 is a point of inflection. And if it's a point of inflection, then f prime at 0.75 must be a max or a minimum. Okay, I think we have enough information to graph this function. So let's put in our zeros of the derivative function f prime at 0. So that's got to be a 0 right there. Okay. F at 1.2 has to be a 0. Okay. And then f at 0.75 has to be a maximum or a minimum. Now let's look at our sign table. Well, f prime at x is negative before 0, so it looks like it's f prime at x has to stay negative before 0. And then between 0 and 1.2, it still is negative, but then from 1.2 onwards, it is positive. Okay, so we have something like this. Now, the reason why I didn't draw this right here is because at 0.75, what aligns with this right here, I should have a max or minimum. So it's going to be a minimum, and it's going to come back up like this. Okay? And there we go. There's the graph of f prime at x. One thing that you should note here is that f at x, so the pink function right there, or the red function, f prime at x is a quartic, likely a quartic. Okay? So therefore, f prime at x, the derivative, which should be 1 degree less than the original function, is a cubic, and you can see it has the shape of a cubic. Let's keep going. This one's a little trickier. We're given the derivative function, and now we have to sketch a graph of the original function. Now note, if we have the derivative function and we have to go back to the original function, we actually have infinite possible vertical positions. So the shape of the graph will be the same, but we don't know if it's shifted up or down, because when we take the derivative of a vertical shift, we end up with 0. Okay, so let's do a little bit of analysis here. Our f prime at x is a cubic, so that means that the original function that we're going to have to draw should be a quartic. Okay, a few things that we note. Okay, f at 3.5 right here. Sorry, apologies. F at 3.5 right here. Okay, so f prime at 3.5 is equal to 0, and we can see that it's going from negative to positive. So it's going from negative to positive. So we have a 0, and the first derivative goes from negative to positive, so the function was decreasing to increasing. So therefore, f at 3.5 is a, and if the function is going from decreasing to increasing, is a minimum. Okay, let's look where else we have. We've got this right here. F prime at 0 is equal to 0. So therefore, and we have it going from positive to negative right there. The first derivative is going from positive to negative, so I'll put that right there. First derivative is going from positive to negative. So f at 0 should be maximum, because the first derivative is equal to 0, and there's a sign change in which it goes from positive to negative, so the original function was increasing to decreasing, so f at 0 is a maximum. F prime at negative 3.5 is equal to 0, so that's this point right here, and we can see it goes from negative to positive. Okay, so that's the same thing as we saw before, so that means that f at negative 3.5 is a minimum. Okay, so I've got two minimums and a maximum. What else do I see here? Okay, so if I have this right here, okay, I've got a maximum, so f prime at negative 2 is a maximum. And it's going from increasing to decreasing, right? The derivative function is increasing and now it's decreasing. So that means the second derivative is going from a positive value to a negative value. So that means that f at negative 2 is a point of inflection. And because the second derivative is positive and then goes to negative, so it's going from concave up to concave down. Okay. F prime at 2 is a minimum. That's this one right here. And as you can see, it's going from decreasing to increasing. So my second derivative is going from negative to positive. And so that means that f prime at 2 is a POI. And it was going from concave down to concave up. We know that based on the sign of the second derivative. Okay, so I think I have enough information. And again, it doesn't really matter where you place this vertically. There's infinite possibilities. So at this point right here, negative 3.5, I need to have a minimum. So I'll put my minimum right here. Okay. Then at 2, at negative 2, I have to have a point of inflection, and then I've got to have a maximum, and then I have to have a point of inflection, and then I have to have a minimum. And so I can draw my graph as follows of the original function. So I come down to a minimum. Now I'm going to be concave down, back to concave up, and there we go. And as you can see, for my original function, y is equal to f at x, I have a quartic shape. Okay, last one over here. Sketch a graph of y equals double prime at x, given the function of y equals f prime at x. So effectively, I have f prime at x, and I need to find the second derivative graph, okay? This is pretty straightforward. You can treat the second derivative as the next order derivative of the first derivative. So basically the first derivative is the same thing, like the treatment that you're going to give it is the same as you would treat going from the original function to the first derivative. Okay, so let's take a look. And what I mean by that is f prime at x is a cubic. So that means that f double prime at x is going to be a quadratic. Okay, I've got some maximums here, and I got a minimum. So I've got some relative extrema. So that means if f prime at negative 2 is a max, then that means that f double prime at negative 2 is 0. Okay, and then over here, f prime at 2 is a minimum. Okay, so that means that f double prime at 2 is a 0. Okay, so I can put my zeros right here. Okay. And then over here, I've got essentially a point of inflection right here. Okay, so then that means that that should be a max or a minimum. So the question is this opening up or is this opening down? And we can use a sign table to find that. So let's go x less than negative 2, between negative 2 and 2, and then x greater than 2. So if f prime at x is increasing on this interval, then that means that the second derivative is going to be positive. If f prime at x is decreasing on this interval, then the second derivative is negative. And if f prime at x is increasing again on this interval, that means that the second derivative is positive. Okay, so I'm going from positive to negative to positive. That answers my question. I am indeed opening up right here. Okay, so if this one right here was y is equal to f prime at x, and that makes this one y is equal to f double prime at x. My original function was a cubic. The next order derivative was a quadratic opening up. Homework is listed there. Thanks for watching.